Any questions from the previous class? Okay. In the last class, I defined some sets based on functions. Right. So one was the notion of a sub-level set, which is the set of all points. So if you have a function f from R to the Rn to R, then the set of all points for which f of x is less than or equal to some particular alpha is called the alpha sublevel set corresponding to that function. And we saw that if the function is convex, then all sublevel sets are convex. But more importantly, I defined the epigraph, which is the set of all x comma y such that f of x is less than or equal to y. And as we saw, there are these deep geometric connections between the epigraph of a convex function and the function itself. For example, many statements for convex functions can be stated in terms of properties of convex sets, stated in terms of the epigraph. Right? So one such property that we saw was that if I have the first order test for a convex function could be translated in terms of the supporting hyperplane theorem for convex sets for the epigraph. Right? So the function is convex if and only if its epigraph is also a convex set. We'll see a couple of other examples where there is this natural connection between the epigraph of the function and some property of the function itself. Okay. Right. So in the last class, we saw how to determine whether a function is convex or not, some necessary and sufficient conditions for convexity. And now we'll see some ways of generating new convex functions from old convex functions. How do you combine different convex functions to produce a new convex function? And one example that we've seen previously is that conic combinations of convex functions are convex. So if you have f1, f2, fm, all functions from, let's say, Rn to R, and each fi is convex, then any f of x defined as summation I equal to 1 to m say theta I fi of x for any theta 1 up to theta m, all being greater than or equal to 0, this function is also convex. Right? And it's easy to see why this is the case. You just take f of alpha x plus 1 minus, say, f of alpha x1 plus 1 minus alpha x2, and then apply convexity to each of those component functions. All right. So that is fairly straightforward to see, but this has pretty interesting applications. Right. So for example, we know that f of x, the univariate function, equal to x square is convex. All right, which means that the function on a vector f of x equal to the norm, the 2 norm of x the whole square, this is also a convex function. Right, because I can write this as a sum of convex functions. Right. Similarly, the function, the 1 norm, which is again a sum of I equal to 1 to n mod xi. This is also a convex function. Now, of course, you could verify all of these separately using some other properties. For example, to verify that the 2 norm of x the whole square, this is a convex function, you could potentially construct the Hessian and show that that is positive semi-definite. But in many cases, approaching it using, say, this particular procedure, that is trying to represent it as a composition of functions or some combination of simpler functions, turns out to be easier. Okay. Another way of generating new convex functions is by taking compositions of affine and convex functions. So what is a convex? What is an affine function? Yeah. So any a times x plus b. So this G is a map from, let's say, Rn to Rm. So this is an affine function. And let us say that H from Rm to R is convex. Then G of H of x is convex. Right? Why is this true? I'm sorry, I should say H of G of x. This is a convex function. Let's simply apply the definition of convex functions. All right, so consider any x1 and x2, right, which lie in the domain of H of G of x, and take any alpha between 0 and 1. Okay, what would be H of G of alpha x plus, or alpha x1 plus 1 minus alpha x2? This is equal to H of, you know, the exact form of G of x, right? It's an affine function, so you can always write it as a times x plus b. So this is a times alpha x1 plus 1 minus alpha x2 plus b, right? What can I do next? This is of course equal to H of alpha times ax1 plus 1 minus alpha times ax2 plus b. Right? Because after all, it's a times x is a linear map. But I can also write b as alpha times b plus 1 minus alpha times. So this is nothing but H of alpha times ax1 plus b plus 1 minus alpha times ax2 plus b, right? Now I can call this some y1 and this y2. I have something of the form h of alpha y1 plus 1 minus alpha y2. I know that h is convex. This is less than or equal to alpha times h of y1, which is ax1 plus b plus 1 minus alpha times h of ax2 plus b. But ax1 plus b is nothing but g of x1 and the other is g of x2. Right? So the composition is convex. But this is true only if g is an affine function. I'm not making this statement for general convex functions g. We investigate that a little further, but this holds purely because g of alpha x1 plus 1 minus alpha x2 is nothing but alpha g of x1 plus 1 minus alpha g of x2. That's an equality. Right? Now, another useful way of combining functions is taking maximum or supremum of different component functions. Okay, so suppose I have f1 from Rn to R, f2 of from Rn to R, then the following function f of x equal to maximum of f1 of x and f2 of x. This is always a convex function. So, of course, assuming that f1 and f2 are convex. Minimum? No.
So if it is that function, it will be directly convex.
No. No. So the minimum of two functions is not convex. If f1 and f2 are, okay, try to get that directly from this statement. Suppose that f1 and f2 are convex. Okay. Minus f1 and minus f2 are concave. So the maximum of f1 and f2 is the same as the minimum of minus f1 and minus f2. Right? So if f1 and f2 are concave, then the minimum is also going to be concave. If f1 and f2 are concave. Yes. So let's see what these functions would look like. Suppose I have two convex functions, right? Let's suppose that this is one convex function, right? This is my x, this is my f1, and let's say this is my f2. what would be the maximum of these two functions? What would that look like? Yeah, correct. So in this case, the maximum would look something like this. Right? So the pink curve would correspond to the maximum of these two functions. But what would the minimum correspond to? That would be the following green curve. Right? At least visually, it looks like the pink curve is convex, right? Both the two curves, F1 and F2, were convex. The pink curve looks convex, but what can you say about the green curve? It's neither convex nor concave. So in general, if I have F1 and F2 both being convex, then the minimum of those two functions need not be convex or concave.
We need to have the condition.
So again, I'm not come to supremum yet. When you have only two, right? So it's a max. You have only two terms to compare with. So it's always a maximum, right? Correct. I'll come to that in just a little bit. Hold. So if I have finitely many functions, then it's obviously the maximum is always achieved. So it's always a maximum of finitely many functions. But it's also true that the supremum, suppose I could also define a function, let us say f from say Rn cross R to R. So in general, I could have some f of x comma y, right, where y takes values in any arbitrary set. Okay, any arbitrary set, doesn't have to be convex, doesn't have to be finite. It could be a continuous set, it could be an interval, or it could be a more complicated set. But suppose that f of x comma y has the property that for each y, f of xy is a convex function of x. So suppose f of x comma y is a convex function of x for every y. Now I can define g of x as the supremum over all possible y of f of x comma y. Right. So here I could be taking the supremum over an infinitely large set. So this function is always convex. You can think of this as a generalization of my previous statement. So in this case, y, you can think of y taking one of two values, 1 or 2. So if y equal to 1, then f of x comma 1 is f1 of x. If y equal to 2, then f of x comma 2 is equal to f2 of x. But more generally, I could have a collection of infinitely many functions and I take the supremum over all those functions for each x. Right. So in this case, suppose I had a third function. So in this case, the maximum of these three functions would look something like this. You can think of maximum of m functions or the supremum of infinitely many functions. I'm sorry? So y, let's assume that y takes only two values, 1 or 2. That's how we're defining it, right? I define f of x comma 1 to be equal to f1 of x. I define f of x comma 2 to be equal to f2 of x. Correct. That's an index set. So if I take f of x comma 1 to be equal to f1 of x and f of x comma 2 to be equal to f2 of x, okay, then the maximum of y in 1 comma 2 f of x comma y, this is nothing but the maximum f1 of x and f2 of x. Just that.
Can we write that practically like over the x, we're trying to maximize the value of both f and x. Like,
for each x,
f1 of x and f2 of x.
Yes.
And over the range of x on r power n or r, we can try to maximize the values. Like we can compare and maximize the values.
Correct. So it's a point-wise maximum. Right? For each point x, I'm finding the maximum of these two function values, and I treat that as my new function.
That makes sense.
Yes, that is what this is. Any other questions? So if y takes on finitely many values, then it's a maximum. That is clear. But in general, y could come from some infinite index set. The maximum may or may not be achieved, right? In which case this could be a suprema. Here is sort of a trivial example. Suppose for each x comma y, f of x y is equal to x to the power, or let's say mod x to the power y, right? Now for each x comma y, this is a finite quantity, but then when you take the supremum over all possible y, the right hand side is equal to infinity for every x not equal to 0. So of course it's a trivial example, it's still convex, right? Each of these, for every y, f of x comma y is a convex function of x, but the supremum is also a convex function. Okay, any other questions? Correct, because that my index set, the set where y comes from, could be infinite. It's not a matter of the range of the function, right? So in this case, there is no value of y which achieves the supremum, right? So what is, let's say, g of x is equal to the supremum over all y in R, or let's say my index set could be 1, 2, 3 up to infinity, set of all positive natural numbers, right, of f of x comma y. What is this equal to? This is equal to 0 if x is equal to 0, because 0 to the power anything is always equal to 0, and it's equal to plus infinity if x is not equal to 0. Correct? So it is this function. It's well defined only for one particular value, x equal to 0. Correct? But this function, this is not equal to any of these values for any finite y. Right? You fix a particular x, let's say x equal to 1. What is g of 1? It's equal to plus infinity. But g of 1 is not equal to f of 1 comma y for any y. Correct? So that is precisely why this is not, the supremum is not equal to, is not achieved by any particular f of x comma y. But if you compare that with, let's say, one of these examples, the supremum is always achieved. Right? So for example, if I take f of x x comma y, so this is equal to, let me say, the maximum between, say, mod x and x square. Okay, what would this look like? Correct. So this would be x square for x mod x greater than 1. That would be equal to mod x for x between -1 and +1. Right, so this is what the maximum would look like. So for every single x, it's either equal to f of x comma 1 or f of x comma 2. Correct? So the maximum is achieved. Whereas in this particular example, this is not equal to f of x comma y for any y. That's the only point that I'm trying to make.
X and F2 of X.
Correct.
There, if you're talking in terms of constant to be in terms of y, it makes sense. But if you're talking the constant in terms of x is from minus infinity to infinity, then it will be like it would be supremum, right? There won't be maximum for it.
So I'm taking the pointwise maximum for every x. The maximization is over y, not over x. Right? It's a function of x. The maximum of, so this g of x is a function of x. For every x, I'm taking the maximum over y. Right? I'm splitting the variables into two sets, x and y. Maximization is only performed over y, and what remains is a function of x. That's my assumption. In this particular, in this particular case, y could take one of two values, 1 or 2, but x can be arbitrary. It could be r, it could be rn, doesn't matter. G of x is between, in this particular example, right? Correct. So in this case, I think it should have been, this should be equal to, correct. It should be equal to 0 for x between 0 and, or it should be 0 between x in -1 and +1. Yeah. Thanks. Correct. Wait. Actually, that's not quite right. This would be equal to mod x in the interval -1 to +1. because I'm taking the maximum, right? So in this particular interval, the supremum is indeed achieved, right? For x in the open interval between -1 and +1, the maximum is achieved, and that is by f of x comma 1. But for any x greater than 1, greater than or equal to 1, or less than or equal to -1, the supremum is never achieved by any finite y. If x is equal to 1, sure, so it should be, but if x is greater than 1 or strictly less than -1, then the supremum is never achieved. Any other questions? So again, we've seen something like this when we talked about duality. Right? So recall that we had an original optimization problem that we wanted to solve, a constrained optimization problem, which was to maximize some f0 of x subject to a bunch of inequality and equality constraints, subject to fi of x less than or equal to 0 and hj of x equal to 0, I taking values 1, 2, 3 up to some m, and j taking values 1, 2, 3 up to some k. So given such a constrained optimization problem, we defined the Lagrangian L of x lambda nu, where these lambda and nu were the Lagrange multipliers, one Lagrange multiplier for each inequality constraint and one Lagrange multiplier for each equality constraint. And we defined this as equal to f0 of x plus summation I equal to 1 to m lambda I fi of x plus summation j equal to 1 to k nu I hi of x. Right? So let's look at this particular quantity as a function of lambda and nu. So fix a particular x, fix any x. What kind of a function is it of lambda and nu? It's an affine function, right? It's an affine function from r to the m plus k to r. So for each x in Rn, the Lagrangian L of x lambda nu is an affine function of the pair lambda comma nu. So you just stack lambda and nu to form a bigger vector. So it's a vector in R to the m plus k. Because it's affine, it's both convex and concave. Right? And I defined the Lagrange dual function g of lambda and nu as the infimum over all possible x in the domain. So here I'll assume that the domain is Rn of L of x lambda nu. Right. So I'm taking the infimum of affine functions. In other words, you can think of it as an infimum of concave functions. and the infimum of concave functions is concave. Right? So this is concave. So irrespective of whether f0, f1, f2, all of these were convex or concave, the Lagrange dual function is always concave. So this has a unique maximum. Right, that much is guaranteed. Right?
Previously, we have given the property that y is convex.
Correct.
It is for fixed.
For a fixed x, sorry, for a fixed y, f of x is a f of as a function of x. When viewed purely as a function of x, the function is convex. Yes, for every y. Right. So what I want is for each y, f of alpha x1 plus 1 minus alpha x2 comma y is less than or equal to alpha f of x1y plus 1 minus alpha f of x2y for all alpha between 0 and 1 and all x1, x2 in the domain. Okay, or if you want to interpret it in terms of, let's say, the second derivative test, then you want the Hessian. Again, the Hessian taken with respect to x, f of xy should be positive semi-definite for all x and y. Okay. The important thing to note is that Hessian is taken only with respect to x. You take y to be constant, take all of the second order partial derivatives with respect to x1, x2, x3 up to xn. Sorry? For every y, the Hessian should be this. Or whatever, for all y over which you are taking the suprema. Okay, any other questions? It will be an n cross n matrix for every y. Yes. Okay, so this was the statement, but we still need to prove why this is the case. And again, the proof is pretty straightforward. Let's prove it for two functions. Okay. So let us assume that f1 and f2 are convex. And f of x is equal to the maximum of f1 of x, f2 of x. Okay. And as before, let's just apply the definition of convexity. So take any two points x1, x2 and any alpha between 0 and 1. What is f of alpha x1 plus 1 minus alpha x2. This is equal to the maximum between f1 of alpha x1 plus 1 minus alpha x2 and f2 of alpha x1 plus 1 minus alpha x2. Correct? So first let's just apply the property that both f1 and f2 are convex. I know that both these are convex. So each of these is less than or equal to alpha f of x1 plus 1 minus alpha f of x2. So the maximum should be less than or equal to the maximum of those two quantities. One of x2 and alpha f2 of x1 plus 1 minus alpha f2 of x2. Okay. Again, we can interpret each of these geometrically. So let's keep this in the side. So I have two functions, right? Let's say these two functions. I'm taking some 2 points, right? x1 and x2. For example, let's assume that I take some x1 over here. Let's assume that this is my x1 and this is my x2. The maximum is basically this particular point, right? The maximum of the two functions is basically the function denoted in green. Right? So this, if I look at f of alpha x1 plus 1 minus alpha x2, let's assume that this is alpha x1 plus 1 minus alpha x2. This is f of x1, and let's say this is f of x2. So f of alpha x1 plus 1 minus alpha x2 would be, let's say, this particular point here. Okay, this point on the green curve. Now, what about f1 of alpha x1 plus 1 minus alpha x2? That would be, okay, maybe this was not such a great point. Let me move this a little bit. Let's suppose that this is my x. So this is my alpha x1 plus 1 minus alpha x2. So f of alpha x1 plus 1 minus alpha x2 would be this particular point. Right, this point over here. This is equal to the maximum of f1 of alpha x1 plus 1 minus alpha x2 and f2 of alpha x1 plus 1 minus alpha x2. Right? So this is my f2, whereas this is the value of f1 evaluated at the same. This is my f1 of x, this is f2 of x. This is less than or equal to the maximum of these two quantities because each of these are convex, right? So what is alpha f1 of x1 plus 1 minus alpha f1 of x2? That would lie somewhere on the straight line joining these 2 points. Right. So recall that the line joining the 2 points is always lies above the curve. So this is the straight line joining these 2 points on the first curve. And this particular value would be on the straight line joining the 2 points on this particular curve. Right? So this is, it would be some point on this curve. So effectively, these 2 straight lines form an upper bound on the actual curve f of x. That's sort of the geometric interpretation. So we have this. So f of alpha x1 plus 1 minus alpha x2 is less than or equal to maximum of these 2 quantities, right? But I also claim that this is less than or equal to alpha times, okay. So each of these is a sum of 2 functions, correct? I claim that this is less than or equal to the maximum alpha f1 of x1 alpha f2 of x1 plus maximum of 1 minus alpha f1 of x2 plus comma 1 minus alpha f2 of x2. Why is this true? Basically what I'm saying is that the maximum of, let's say, some alpha, let me use something else, a plus b comma c plus d is less than or equal to the max of a comma c plus max of b comma d. Right? It's just that. B comma d. You take any 4 numbers a, b, c and d. The maximum of a plus b and c plus d is less than or equal to the maximum of a and c plus the maximum of b and d. Alright. But what is the first term equal to over here? This is just alpha times the maximum of f1 of x, f1 of x1, f2 of x1 plus 1 minus alpha times the maximum of f2 of f1 of x2 and f2 of x2. Which is just alpha times f of x1 plus 1 minus alpha times f of x2. Okay, any questions? Again, there are only two main things we used. One, that each f1 and f2 are both convex. And the second is that the maximum of a plus b comma c plus d is less than or equal to the maximum of a comma c and maximum of b comma d. Nothing else. Right? But a nice consequence of this particular property is that if you take any set of affine functions, right? If you take the maximum of all of those affine functions, or even the supremum, that always results in a convex function, right? But the maximum supremum of any set of convex functions is always convex. So affine functions always also convex. Now you may wonder why I'm bringing this thing up. The reason I'm bringing it up is, suppose I give you an arbitrary convex function, let's say a convex function on R. Okay, is it possible to write it as a maximum or supremum of potentially infinitely many affine functions? How? Okay, exactly. So you consider the tangent at all possible points. Okay, so let us define. Right, so this is my f of x, and let me define my g of x comma y as the tangent to f of x evaluated at the point y. Right, so it's a tangent to f at y. Now we've seen from the first order principle that the tangent is always a lower bound for the function, right? And it passes through f at exactly one point. Right? So now if I take another, let's say g bar of x to be equal to the supremum over all possible y of g of y, sorry, g of x comma y, you know that for every y, g of x comma y is always less than or equal to f of x. Correct? And this passes, so obviously g bar of x should be less than or equal to g of x comma y. Sorry, should be less than or equal to f of x. And g bar of x is guaranteed to be convex. Right? But this is actually equal to f of x. Because if you take any particular point x, right, this is always less than or equal to f of x, but there is exactly one y for which g of x comma y is equal to f of x. Because the tangent passes through, there is at least one tangent that passes through y. So in fact, this inequality is an equality, because there is one tangent that passes through this particular point. Right? Supremum over y of g of x comma y, right? It's in fact going to give you f of x. I'm sorry?
Arc max, then
Correct.
what is the value of y that
It is going to be, so this in fact will turn out to be equal to x. Right? So the one that achieves this supremum will be y equal to x.
you take a tangent at that point?
Exactly.
Corresponding x further.
Exactly. Yes. The tangent that takes the maximum value at a given x will be the tangent passing through x comma f of x itself. Again, this is only a geometric intuition that I'm giving you. I'm not proving this particular statement. Right. So in fact, as long as the function is sufficiently nice, you can write any sufficiently nice convex function as the supremum of infinitely many affine functions. Right? But this also has an interpretation in terms of the epigraph. Right? If you recall, when we talked about convex sets, we saw that most convex sets could be written as an intersection of half spaces. Now similarly, you can think of this for every tangent you have a half space. So the intersection of all of these half spaces basically gives you the epigraph. So that's a way of interpreting this particular statement. The boundary of the epigraph will be the convex function. All right. Any questions? Okay. So previously we saw that the composition of a convex function with an affine function is always convex. But what if I have two general functions? So I have, let us assume that I have some h from, let's say, Rn to Rm and g from Rm to R. So when can we guarantee that f of x, which is just the composition of these two functions, g of h of x, so when is this convex? Let's take an even simpler example where both h and g are functions on R. Okay, how would you try to approach this problem? So what I'm looking for is a set of sufficient conditions on h and g such that g of h of x is convex. Right? Yeah. Can you say that if h and g are both convex, then f of x is always convex?
The sufficient would be h of r plus 1 plus 1 minus r plus 2. If g is convex
Correct.
and h of r plus 1 plus 1 minus r plus 2 is equal to
But when can that happen?
yeah.
Only if it is affine, right? So surely if h is affine, then we're done. We don't have to worry about it. But can we come up with other conditions? Okay, we'll assume that the range of h and g are both convex. Both the range and the domains are convex sets. Okay. So again, we're looking at functions on R, right? What is the easiest test to see if a function on R is convex or not? The second derivative test. Okay, so what would be the second derivative of f? So what is this equal to? Yeah, so it's g, the first derivative of g evaluated at x times, okay, sorry, g dash of h of x into h dash of x. That's it. I'm sorry. This is the first derivative. But what about, I'm asking for the second derivative. Right? So second derivative of f evaluated at x is equal to, correct, so g double dash of h of x, h dash of x the whole square plus g dash of h of x times h double dash of x, right? So if this is greater than or equal to 0 for all x, then f is going to be convex. Okay, so what problems can we run into? If g is convex, then we know that g double dash is always convex. But what can we say about this particular quantity? So if g and h are both convex, then g double dash is greater than or equal to 0, h double dash is greater than or equal to 0. But g dash of h of x could potentially be negative, right? So what is a sufficient condition? Correct. So if g is monotonically increasing and convex, and h is also convex, then f is convex. So if g is convex and at least non-decreasing, and h is also convex, then f is convex. Any other conditions? Any other condition under which f can be convex? Suppose g is still convex, okay, and maybe it's monotonically decreasing or non-increasing. Correct. If h is concave, correct. So if g is convex and monotonically decreasing, and h is concave. If it's convex, then this quantity is always greater than or equal to 0. H prime of x, the whole square, this is always greater than or equal to 0. Since g is monotonically decreasing, this quantity is negative. And if h is also concave, then this is also negative. So this quantity is positive. So this whole quantity is positive. Now what if g is concave? Suppose G is concave and increasing. Yeah, and H is concave. Then this quantity is negative, right? This is increasing, so it's positive. This is negative, so the second derivative is negative, which means that this is a concave function. Now similarly, if G is concave and decreasing and H is convex, then F is concave. Right? But note that we proved all of this assuming that the first and second derivatives exist. But all of this holds even if the derivatives don't exist. Okay. So this was a way of guessing that whether, like, what are the conditions under which F is convex or concave. But you can prove this from first principles. Right? So let's just try to prove the first set of conditions. So let G be convex and increasing and H be convex. We make no assumptions on the differentiability of either G or H. So let's look at f of alpha x1 plus 1 minus alpha x2. This is just G of H of alpha x1 plus 1 minus alpha x2. Now we know that H is convex. So H of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha H of x1 plus 1 minus alpha H of x2. But we know that G is monotonically increasing. So if this quantity is H, if H of x is less than or equal to alpha H of x1 plus 1 minus alpha H of x2, then G of this is going to be less than or equal to G of alpha H of x1 plus 1 minus alpha H of x2. So this is less than or equal to G of alpha H of x1 plus 1 minus alpha H of x2. So here we've used the property that G is increasing and H is convex. Now you just use the property that G is convex. This is less than or equal to alpha G of H of x1 plus 1 minus alpha G of H of x2. Right. So we've seen a bunch of different ways of generating convex functions. Okay. And this turns out to be very useful because let's take, for example, if G is convex, then e to the G of x is also guaranteed to be convex. Right. Then e to the G of x is convex. Similarly, if let's say G is concave, and positive, then log of g of x is concave. Once again, you can try to guess the convexity or concavity of 1 by g of x, or even g of x whole to the power p for some positive integer p. And now sums of, so if g is, let's say, a vector valued function, so I have g1, g2, g3 up to say gk, then summation I equal to 1 to k gi of x whole to the power p. You can now derive conditions under which this function is convex or concave. Right. You can also construct slightly more complicated examples. So suppose I give you an arbitrary vector. So the function f from say Rn to R defined in the following way. So f of x is equal to the sum of k largest components of x. I claim that this is a convex function. Why is this convex? Can you do that? How would you take max iteratively? So if it is just the largest component of x, if k equal to 1, then you see that it's a convex function, right? Because I can express this, I could define so if k equal to 1, then I can define fi of x to be equal to just xi, right? Just picks the ith component. So f of x would just be the maximum for I equal to 1, 2, 3 up to n of fi of x. Each of these is a linear function. So this would be a maximum of linear functions and hence convex. But I'm asking for the sum of k largest components of x. But sure, the sum of convex functions is convex. So which functions are you going to look at? So I know that the largest component of x, that is a convex function. Are you sure that the second largest component, so let's define a new function, f of x, to be just the second largest component of x. Are you sure that that is going to be a convex function? Correct.
I remove that largest component from the set.
Correct. Which is equal to the second largest, which is exactly equal to the second largest component of x. Right? Are you sure? In general, it's not. But I'm saying that the sum of k largest components of x is convex.
If we take a vector x and multiply it in find k largest.
Okay, you're thinking along the right lines, but can you be a little more precise? Correct. Which affine function will you consider?
once to extract the rest.
I'm sorry?
Like
Okay,
once,
sure.
once along the diagonals to extract like the large the rest.
Okay, so how many functions are you going to consider? No, you're guessing. Correct. Exactly. So let me define, let's say, f I of x. So I is basically any subset of, so out of n I pick k components, and this is equal to j in I xj. So you look at all possible combinations of k components and sum them up. So for example, if x lies in, say, R3, and I'm looking at the sum of two largest components, then this would be x1 plus x2, x1 plus x3, and x2 plus x3. So this would be my first function, this would be my second function, and this would be my third function. Right? Now each of these is an affine function, it's a linear function, right? So the maximum over all I, fi of x, this is exactly equal to f of x, the sum of the k largest components. Right? So this is going to be convex. I'm sorry?
Solving this problem is equal to
Sure, it is a linear program. But this doesn't even have any constraints. Okay. Now, okay, so maybe this is a good point to stop. Any questions? Correct. Let's see, I'll try to maybe give a proof in the next class, or at least give a link to the proof. Any other questions? Okay, so let's stop here.